Now we will see how to design digital filters by using bilinear transformation, which is called BLT. So steps involved in this is, first step, what we have to do is, from the given specifications, the same, we have to calculate its analog frequency, the transfer function HA of S we have to calculate. So then we have to calculate pre-wrapping analog frequency using the formula ohm is equal to 2 by T into tan of omega by 2. Using this we have to calculate ohm, okay, frequency in radian per second we have to calculate. And after this, second step, what we have to do is, using analog frequency, first we have to go ahead with this frequency and then we have to calculate HA of S. So after calculating this transfer function, what we have to do is express this HA of S into H of S, which is analog to a frequency domain, and then what we have to do is select the sampling rate. Okay, third step, what we have to do is select the sampling rate of a digital filter, which is T in seconds. Okay, so in seconds per sample we have to calculate. So that means we have to assume, or we can consider this point. So most of the time they will be providing this, and most of the time they will be providing this as well. So directly also they will provide this. It means directly next step is we have to apply BLT method, that is nothing but bilinear transformation, to find the H of Z. So how to calculate this? So he is just substituting S as 2 by T into 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1. Only in the place of S we have to substitute 2 by T, 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1. So we will see an example, then we will understand. Actually, compared to our IIT, it is easier. We will see an example. The transfer function of an analog filter is H of S is equal to 1 divided by S plus 1. Obtain the transfer function of the digital filter using bilinear transformation. Assume sampling duration of 1 second. So from this what we can get is H of S they have given directly, which is 1 by S plus 1, and digital filter using bilinear transformation method. So for T sampling duration of 1 second, means T also they have given. So for this example, H of S is equal to 1 divided by S plus 1, T is equal to 1 second. So in this case what we have to do is, everything they have provided, so what we wanted, right? So now directly we have to express or apply the technique. How to apply? H of Z will be equal to, in the place of we substitute S as 2 by T here. 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1. In this H of Z is equal to, H of S we have this, okay, H of S is 1 divided by S plus 1. Now we will substitute S value, okay, S in the place of S, 1 divided by S, which is 2 by T into 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1. Okay, so now we will simplify this. So T is 1 second, which is nothing but 1 divided by 2 into right, 1 minus Z raised to minus 1 divided by 1 plus Z raised to minus 1. Okay, so in this case what okay, so this is S, 1 divided by, this is S plus 1 we have, right? So 1 divided by, this in the place of S, okay, in the place of S we have substituted this value. So 1 divided by S plus 1. So this is 1 divided by S plus 1. Okay, so now what we have to do is, further is simply simplification. We will simplify this, which is equal to 1 divided by 2 as it is, 1 minus Z raised to minus 1 plus. So we will take this here and make a denominator same, which is 1 plus Z raised to minus 1 whole divided by 1 plus Z raised to minus 1. So this Z raised to minus 1 plus Z raised to minus goes to the numerator. So which is 1 plus Z raised to minus 1 goes up, and then down we have 2, means in the denominator we have 2 into 1 minus Z raised to minus 1 plus 1 plus Z raised to minus 1. So we will simplify this, which is 1 plus Z raised to minus 1 2 into 1 is 2, 2 minus 2 z raised to minus 1 plus 1 plus z raised to minus 1. We will simplify this bit more. 1 plus z raised to minus 1 as it is divided by 2 plus 1 is 3. Okay, 2 plus 1 is 3 minus 2 z raised to minus 1 plus z raised to minus 1, which is minus z raised to minus 1, which is h of z is equal to. So this is our bilinear transformation. We'll have another example, which is now calculate design, or you can say apply BLT for the system. H of s is equal to 2 divided by s plus 1 into s plus 2. Okay, for t is equal to 2 seconds. How we can apply the bilinear transformation? As we said, it is quite easy. Just we have to substitute in the place of s by s has to be substituted by 2 by t into 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1. Okay, so now we have 2 divided by this. So in the place of s we have to substitute. S is 2 divided by t into 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1. Okay, so this is s. Okay, this is s plus 1. This is first term. Second term is, it is human tendency to forget this, right? Completely, once we write plus 1 we forget. Please don't do that. Even I did in the earlier case, right? So s is again 2 by t into 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1. This is s plus 2. Okay. Further is simply simplification. For t is equal to 2 seconds, so we can substitute t equal to 2 here. Once you substitute t is equal to 2, so it is 2, and then this is also 2. So 2 ones are 2 to get cancel each other. So then further, as I said, to just to simplify, so it is nothing but 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1 plus 1 into 1 minus z raised to minus 1 divided by 1 plus z raised to minus 1 plus 2. Okay, so this one is 2 divided by 1 minus z raised to minus 1 plus simplification 1 plus z raised to minus 1 divided by 1 plus z raised to minus 1, right? Next into 1 minus z raised to minus 1 plus 2 into 1 plus 2 z raised to minus 1 whole divided by 1 plus z raised to minus 1. So these two, 1 plus z raised to minus 1, 1 plus z raised to minus 1, these two goes up, which is 2 into 1 plus z raised to minus 1 into 1 plus z raised to minus 1. We can write as square of that, right? 2 into 1 plus z raised to minus 1 whole square divided by, so this is 1 minus z raised to minus 1 plus 1 plus z raised to minus 1. So this get cancelled, right? Which remains only 2 into, so in this case 1 plus 2, which is 3, minus z raised to minus 1 plus 2 z raised to minus 1, which is plus z raised to minus 1. Okay, 2 get cancelled. So we can write 1 plus z raised to minus 1, sorry, z raised to minus 1 whole square divided by 3 plus z raised to minus 1, which is h of z. This is bilinear transformation technique to find out or to design the digital filters. Okay, digital filters. There are two methods we have discussed to design the digital filters of Butterworth, we can say. So here we have, one is impulse invariance technique or transformation, and bilinear transformation, which is called IIT and BLT. Okay, these two are the techniques and to design the digital filters. Now we will solve one more numerical to design the analog Butterworth filter, okay, which is HA of S we call, right? So to design this, as we have followed the steps, saying first we should have a KP and OMP and KS and OMS, which is passband gain and passband obviously frequency, and then this is stop band gain and then stop band frequency. So when we have these things, usually they note they'll provide these datas, okay, KP, KS, OMP, OMS. So through this we will find out the first n order of the filter, and then based on that n we are going to use the formula HA of S is equal to So ohm c square, ohm c to the power n divided by, this is divided by, we have summation of s minus sk, where this sk represents number of poles, and number of poles will be dependent on the number of order of the filter, and k is from 0 to 2n minus 1. Okay, so when we have that case is okay. Now this is quite different. So for the given specification, design analog Butterworth filter. Here neither they have given Kp nor they have given Ks, ohm P and ohm S. So in this case, how to deal with this? So first we require Kp. For that, passband gain. So this is about your passband, because this is Fp, it is Fp, and this is Fs, means passband frequency and stop band frequency. So this is a delta P, okay, and then this one is our delta S. So by using this delta P, delta S also we can calculate. So Kp is equal to 20 log of delta P is our formula. Kp is equal to 20 log of delta P. Most of the time Kp they will provide. If not, we have to use this formula, 20 log of delta P. When we substitute this, 20 log of 0.8 comes minus 1.938. Okay, this is our Kp. And similarly, we want ohm P also. Will wait. Ks is equal to same 20 log of our delta S, which is called, which can be substituted 20 log of 0.2, which gives us minus 13.98. Okay, these two are Kp and Ks. Next we have to calculate ohm P. Ohm P is nothing but our omega. Okay, so omega is nothing but 2 pi f. So f with respect to passband, so we will take it as 2 pi fp. So since 2 pi is known factor and fp is given here, which is 1000 hertz, so into 1000 hertz, which comes 2000 pi. Similarly, we have ohm S is equal to, again this is also omega, is nothing but 2 pi f, only is stop band frequency, which is 2 pi into 5000. They have specified this as 5000 hertz. So which is equal to our 10,000 pi radian per second. This is radian per second and this is also radian per second. Okay. So now, yes, we have got the required data. Okay. Now we have got in what we wanted, all those datas we have received. So now it is easy for us to calculate the order as well as analog filter. Now let us calculate the order. N is equal to, so formula is the ratio of log of 10 to the power of minus Kp divided by 10 minus 1, okay, divided by 10 to the power of Ks divided by ohm P, okay, sorry, Ks divided by 10 minus 1, okay, this divided by 2 log of ohm P by ohm S. This is the formula. Now once we substitute all the values here, it is a ratio of log of 10 to the power of minus Kp is minus plus 1.938 by 10 minus 1, okay, so divided by 10 to the power of Ks. Ks is minus Ks by 10. Minus Ks means minus plus, which is 13.98 divided by 10 minus 1 divided by 2 log of ohm P is 2000 pi divided by 10,000 pi is ohm S. So substitute this and calculate. You get, so you get n is equal to 2. Okay. When we have n is equal to 2, actually we can go ahead with a formula saying h of s is equal to ohm c divided by summation ohm c raised to n divided by summation of s minus sk. Now we have to start substituting k. K is equal to 0, 1 up to 2n minus 1, which is nothing but n is 2. So 4 minus 1, which is nothing but 3. So it is 0, 1, 2 and 3. So among these, only 2 poles will be available, stable. So those two poles only we have to consider. How we are going to consider? Poles which lies in the on the left side of the S plane. So is nothing but minus of value negative, which all poles comes to, those poles we can consider here. So you can calculate it. Else directly you can remember, when n is equal to 2, poles is like, one this one denominator s minus sk will be, you can directly write that saying HA of S when n is equal to 2. Okay, when n is equal to 2, HA of S is equal to ohm C divided by S square plus root 2s plus 1. This you can remember. If you calculate also, we get the same thing, s square plus 2s plus 1. Right, now we have to calculate ohm C. Ohm C is again a formula, ohm P divided by 10 to the power of minus Kp by 10 minus 1 to the power 1 by 2n. When you substitute all these values, saying ohm P is 2000 pi divided by 10 to the power of minus Kp minus plus, which is 1.938 divided by 10 minus 1 to the power of 1 by 2n. N is 2, so 2 2s are 4. Okay, once you calculate this ohms in a calculator, you will get 2309.47 pi radian per second. Okay, therefore HA of S will be, you can substitute ohm C, which is 2309.47 raised to 2n divided by s square plus root 2s plus 1. This is analog filter.